1, 0.
1, 2, 3, 4.
Hi everyone, welcome back. This is section 6.4, part 2 of graphing trig functions. Previous class we took a look at graphing sine, cosine, and we took a couple of examples in terms of how to be able to apply an amplitude and a period and a phase shift and a vertical displacement. So what we're going to do is we're going to continue that right now. So if you take a look at this next example, we're given a sinusoidal function for both parts A and part B, and it's asking us to determine possible equations for the following graphs. So the first thing I'd say is there are an infinite number of possible correct answers for this. And we'll give a couple of examples of what they could look like, but just know that potentially the solution that we give is something that you didn't, that I didn't show here. So if I was to look at this and it says find a possible equation, it's not saying if you want to have a sine graph or a cosine graph. So if we start right here, we could say, well, let's take a look at a sine graph, because right here, starting at 0, 0, that's clearly one full period of a sine function. And it's going from 0 to pi, and it starts at the origin. And let's see what we could do to come up with trying to say what some of the characteristics are. So assuming that going up one space represents 1 unit, we'll say this is positive 3 and this is negative 3, and we begin at 0 and we end at pi. And if we want to say what a sine function would look like for it, there would be no phase shift, and there would be no vertical displacement either, because we're starting at 0, 0. So all we have to worry about is an amplitude of 3 and then compressing our period from 2 pi down to pi. So you could say something like y equals 3 sine, and then I'm just going to write an x right here, and in between the sine and the x we have to apply what our new period would be. So if our regular period is 2 pi and it's gone down to pi, we've had a horizontal compression by a factor of 1/2. And if you have a horizontal compression by a factor of 1/2, then next to the x, you would write a 2x, and that would represent that right there. If you wanted to say something where you're writing your b values and all that stuff, you could always say, well, b equals 2 pi over the period, and the period is pi, so my b value is just 2, and that's how we got that number 2 right there. Now, just to be clear, that's an example of a sine function. We could have also given an example of a cosine function. So cosine looks like it starts always at its high point, which is right here. Now, if halfway between 0 and pi right here would be pi over 2, then halfway between that would be at pi over 4. So we've shifted over pi over 4 units to get to that maximum point here. And then it would just terminate right there. The length of the period would stay the same. The amplitude would stay the same. The only thing that's different is we now have a horizontal phase shift of pi over 4 units to the right, and that's where cosine starts. So we could also say y equals 3 cosine 2 x minus pi over 4, something like that. Okay, if that example made sense, why don't you pause the video right now and see if you could come up with something for example B, knowing that the way it's spaced out is a little bit different. They're saying from 0 to pi is on this graph right here. So if you count the spaces, every single space is going to be 1/12 of the pi. This is 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's 12 spaces to get to pi. So every single space would represent 1/12 of a pi. So just keep that in mind when you're trying to figure out your solution. And if you haven't started to do so already, then what you could say is, whoops, sorry, this is going to be the point, my fault, 0, 0. This is pi over 12, which means right here, that would be at pi over 6 right there. That's the equivalent of saying 2 pi over 12. Try and find a sine and a cosine example. Okay, so for sine, we're going from here all the way to there. There's an example of a sine graph. I'm going to leave the period for the end because I think that's the toughest part to fill in. Sine starting right here at pi over 6, and we've shifted pi over 6 units to the right. So we could say something like y equals 2 sine blank x minus pi over 6, and it looks like the vertical displacement is split equally going above and below from the x-axis, so there is no vertical displacement. So we can just leave it as is. There's no value at the end there that we need to add in. For cosine, our maximum point is right here. So that would be 1, 2, 3. That would be 4 spaces to the right from 0. And 4 spaces to the right would be 4 pi over 12. And instead of saying 4 pi over 12, we could reduce that to pi over 3. And so you could say this would be y equals 2 cosine something x minus pi over 3. So now we have to figure out, well, what's our period here? So let's take a look at the total number of spaces that it takes to complete a period. So if we begin here and finish here, and whether it's sine or cosine, it's going to be exactly the same period. We get 1, 2, 3, 4, 5, 6, 7. It was 8 spaces. So if each space is pi over 12, then our period is equal to 8 pi over 12s. And so they're saying find the b value. Okay, find the b value, knowing that our period is equal to 2 pi over our period, and our period is 8 pi over 12. We could have said 2 pi over 3, and then we will times by the reciprocal. Our pi's cancel each other out, and we end up with 24 over 8, which is just equal to 3. So we have a horizontal compression by a factor of 1/3 to come up with this example right here. Okay, hopefully both of those made sense. Let's move on and let's see what we have coming up next here. Okay, so the big thing now is, are we able to graph sinusoidal functions? Can we graph a sine and can we graph a cosine function? And so something you're going to start to hear me refer to is the acronym DOCP. Sounds like a little bit of a strange word, DOCP. And what that means is there's different ways to go about this, and you may do something different with your tutor. But what we talk about here is we want to look at the parameters, the D value, the A value, the C value, and then the B value, and that's going to tell us exactly what's what I find is maybe the easiest way to be able to graph a sinusoidal function. If you wanted to apply rect from transformations, that would also work. But applying by doing DOCP, you're able to do this all in one go without having to do step 1, 2, 3, 4, 5, and it's a really safe, measured way of being able to graph these examples. So graph one period of y equals 3 cosine x plus pi plus 1. Okay, so because we're still new to this, on the side here, let's just refresh ourselves and make sure that we know that a cosine function looks like this. Okay, and now let's space out what we have with everything here. So here's the point 0, 0. So this would be pi over 2 pi, 3 pi over 2, 2 pi. And every space going up will be 1, and every space going down will be -1 down there. So we'll continue to say that every 3 spaces will represent a half pi, and that's just because based off our special angle triangle ratios and everything that we're going to be working with, it's going to make everything the cleanest it can be. Okay, so DOCP. Right here is our A value. Our B value would be there. Here's our C value, and here's our D value. And so according to DOCP, they would be saying apply your vertical displacement, see what's happening with your up and down values first. And in this example here, our function has shifted up 1 unit. So I'm going to put in a dotted line just to represent that that's what's happening right there. That's going to be your new middle line. That's not an asymptote or anything like that. That's just our new middle line. The A values are amplitude, and our amplitude is 3. And what that means is we're going up 3 and down 3 from the vertical displacement line. So if you go from that 1, you go 2, 3, 4, that's going to be our maximum high point. And then down 3 from the middle line, 1, 2, 3, would be right here. That would be your low point right there. Okay, so we've gone up 3 and down 3 from our vertical displacement. So D, A, C. Now we're going to go pi to the left. So if we want to go pi to the left, we know that every 3 spaces is going to represent moving over half a pi backwards. And we've gone pi to the left, and it's a cosine function. So if this is a cosine function, then we want to make sure that we're going to be able to start off at the high point, because we know cosine starts at the high point. And we know that our period has no adjustment from a normal cosine function. Our period, because there's no value between this cosine and this x, our period is still 2 pi. So that means that if we start at negative pi, if you add 2 pi to negative pi, you would finish right here at positive pi. And so our function will have our start point there and our end point there now in place. So what I like to do is I like to look at some of the key points. Here's our start point for a regular cosine function. Here's our stop point for a cosine function. And halfway through, it's going to be at its minimum value. So if we average out these, we know that right down here, this is going to be where we're going to have a minimum value if it's a cosine function. And then if you half those values between your minimum and your maximums, you would be right on the vertical displacement line. So we have a point right here that's halfway between the maximum and the minimum, and then 1, 2, 3, and then right there, that would also be right in between 2. And so what you could do then is you can graph the rest in, and that would be giving an example of showing one period of a cosine function. So again, there's multiple ways of doing this, but I think this way seems to make a lot of sense to a lot of people when they graph that. Okay, if the previous example seemed to go quite well, you might want to pause it right here and see how this would look. I would preface though that this one does have a period adjustment. We have a 3 for B value, and so that's going to make things slightly more difficult. So here we go, 0. Can always make sure we label our axes so whoever's marking it knows how we're spacing things out. Okay, and on the side here, let's just say there's our basic sine function, just like that. Okay, so DOCP, A, B, C, D. Now, taking a look at something like this, we would say, okay, we're going to go up 1 again. We have an amplitude of 2, so we would go up 2 from there, down 2 from here. And it looks like we're shifting over. Our C value is pi over 2 to the right. And for sine, you start neutral. You start in the middle on the vertical displacement line. So at pi over 2, we're going to be right here. And then where do we finish? So this is a part that's definitely the trickiest. So typically a sine function is 2 pi, but if we have a B value of 3, then we know that our period is going to equal 2 pi over 3. So there's a couple ways to look at it. This is a little bit of a gimmicky way, but see if this makes sense. The way we've structured our graph from 0 to 2 pi is a distance of 12 spaces on this graph. 1, 2, 3, and so on. All the way we would count 12 spaces from 0 to 2 pi. If we have a b value of 3, that means we also have a horizontal compression by a factor of 1/3. And what that means is instead of having 12 full spaces, we would have 4 full spaces to complete a period for sine 3x. So that means that if we started right here, if we count 1, 2, 3, 4, that would represent the period that we want. Now, if you did measure that out, that happens to be 2 pi over 3. And if you're still thinking in degrees, you could say, well, 2 pi over 3 is 120 degrees. Each individual space on this spacing is 30 degrees. So if it's 120 degrees and it's each individual space is 30 degrees, then that makes sense that I would go over 120 divided by 30. I'd go over 4 spaces, so that works out. Now with sine, we have our start point, we have our end point, and then in the middle, we're back right at the vertical displacement line. And then halfway between the start and the middle, we would be at one of our other key points. Now, this is a negative sine graph. So instead of going up, we know that we would go down. And so you would go down to your minimum, and then you would go up to your maximum. So it would look something like that. It's going to be a reflected sine graph, and they're only asking us to graph one period, so that's there, and that should be okay, hopefully. Okay, now that we've had a chance to graph a couple, why don't you pause the video and definitely see how you would fare out on graphing this cosine function. Okay, so mini graph of cosine looks like this. Okay, now in terms of our DOCP, we don't have anything back here. There is no vertical displacement going up or down, so our middle line is the x-axis, and we'll just keep that in mind. Our A value is 2. We have an amplitude of 2, and we know that we're going to have a reflected cosine graph. So instead of going down, we're going to start by going up. But our A value is 2, which means that from 0, we go up to for a maximum, and we go down to for a minimum. We're shifting over pi over 6 to the left. Pi over 6 is one space on the way we've spaced things out, so we're going to go one space over to the left. So normally I would put something right here at the maximum for cosine, but because we have a negative graph, instead of starting up here, we're going to start at its minimum point right there because we have a reflected cosine graph. And then to find our period, to figure out where we're going to end with, we know our b value is 3 over 2. And so again, do whatever makes sense for you. Let's actually find the period by saying, well, the period is going to be equal to 2 pi over b, which is 3 over 2, which means that the period is going to equal 2 pi times 2/3. So the period is going to equal 4 pi over 3. We have a horizontal compression by a factor of 2/3. And so if you think of it as a horizontal compression by a factor of 2/3, and you know your normal period was 12 spaces based off of how we space things, and you take 2/3 of that, then 2/3 of 12 would give us 8 spaces. So beginning right here, if you count over 8 spaces to the right, so 1, 2, 3, 4, 5, 6, 7, 8, we would stop right there, and that's where we're going to have our end point. So we have our beginning, we have our end, and we know halfway through, we normally had our minimum. Now we would have our maximum because this is an upside down cosine function. 1, 2, 3, 4. Okay, so 1, 2, 3, 4. So right here, we would go up to the maximum right there. And then based off of that, we could say, we could average out the minimum to the maximum by going over 2 spaces, and we'd have something here. And There's our cosine function. If you want to think of like some nitpicky things, some pet peeves of math teachers when they're marking is one thing that is really bothering is if you graphed it and you went like this, then that's not good, because this right here is a minimum point and you've gone below your minimum point. So we got a little careless by that. So you want to make sure that as you draw the sinusoidal shape, it starts to curve back around this way here. Ideally, you'd put some sort of arrows, depending on what your teacher's looking for exactly. Okay, so now we got a couple examples. We're saying, let's find the period of each of these functions, and maybe we could generalize some sort of pattern that emerges from this. Okay, so we know that our period is going to equal 2 pi over the b value, and in this case, our b value is a little strange. It's 2 pi over 2. Well, if you have 2 pi divided by 2 pi over 2, that'd be like saying 2 pi times 2 over 2 pi, and we'd be just left with 2. So that means that in this case, our period equals 2. And the reason that there's no pi in it is because the pi got divided out because we had pi as part of our b value right there. And anytime that you have a 2 pi on top with a sine or cosine function, if you have 2 pi on the numerator, whatever the denominator is going to end up being your period. So instead of doing the calculations that we did in part A every time, we can now say, hey, that says 2 pi, this says 2 pi. We can just say that means that we would have something in which we could say our period equals 3. And then for our next example here, we could say our period equals 4. And if they want to say, well, what would happen if you had something where you wanted to create a cosine function with a period of 5? We could probably do that pretty easily too. You could say y equals cosine 2 pi x over 5. Okay, a couple more examples now. So what would it look like if we were to graph one of those functions in which our period now doesn't have a pi in it, but it's just some sort of integral number? So we have that in this example here. I would note that I think that it probably looks a little bit awkward. I would say you could rewrite this equation as saying y equals 3 sine 2 pi over 8 x minus 2 plus 1, and that means the exact same thing as what you have right there. So probably the version that we just filled in on the right might look a little more common actually. Okay, well, let's go about this. Now, we always start our questions by labeling the x and y axis, and when we take a look at this, I would say our period is going to be 8. And so if our period is going to be 8, we don't want to say every 3 spaces is a half pi, because if we wanted to average that out and try and figure out what it would look like, that'd be very, very difficult. Knowing also that half a pi over 2 is approximately 1.57, and it might be a little awkward trying to figure out exactly if that would fit on the graph or not. So these questions may actually become easier, because what you can do now is you can just say every space is representing 1 unit. And so you could say it's as easy as saying, hey, this is 1, here's 2, I'll label every second unit. And that's going to be easier to fill in than what we had from before. Our vertical displacement in this question is 1. Our amplitude is 3. So from our displacement line, you go up 1, 2, 3. We go down, we go down 3, 1, 2, 3. Okay. And we're going to say our C value is 2 units to the right. So it's a sine function. We know that sine looks like that. So we can say here's 2 units to the right here. And then based off of that, we know that we could go, our period's 8. So if we start at 2, we're going to end at 10. Halfway would be at 6. That's 4 units in between. And then if you average that out, you'd be going up to your maximum. And if you average out the second half here, you'd be going down to your minimum. And now we can start to get pretty efficient at graphing these sinusoidal functions. Okay, and so there you have it. That's graphing a sine function where you now have a period that doesn't have pi in it. Okay, so let's try one on our own here. Here's a mini graph of cosine. Again, let's pause the video, see what you guys come up with, and I'll do the same. Okay, so one thing you might have noticed is what happens if it says pi over 4? Well, you could calculate it. You could also say, hey, let's times the top by 2 to make it say 2 pi, and then let's times the bottom by 2. And so you get 2 pi over 8, and then that works out just exactly the same, and that's fine. So if you wanted to, you could have that. And we know that our period, once again, is going to be 8 in this example. Our vertical displacement is at -1. Our amplitude is 2, so you go up 2 and you go down 2. And it's an upside down cosine function. And so based off of that, we know we're going to start by going 3 to the left. So we go back 3, and we're going to start at the minimum point because we know it's an upside down cosine function. And if our period is a distance of 8 units, then if we were at -3, we'll end at +5. We average that out, and we can now come up with our remaining values. Okay, and that would be our upside down cosine function right there. Okay, so example 10, write an equation for the following graph in terms of both sine and cosine. Let's apply our DOCP. Our maximum here is at 1 and our minimum is at -5. So our average, our displacement line here would be at -2 because we would be going up 3 and we'd be going down 3 from right there. So we know our displacement, our d value will be -2. Our amplitude will be 3, and if we want to do a sine function, depending if we want to do a negative or a positive sine function, I think probably a positive sine function is a little bit easier. Then let's start right here at -1, knowing that again, you could have started somewhere else. You could have started at 3, but that looks like that makes sense. And we could say y equals, okay, amplitude of 3 sine, let's leave the period for last, x plus 1 because we've gone 1 to the left, and a displacement of down 2. And our period, if we started at -1, we're finishing at +3. So we have a distance of 4 units. So you could say 2 pi over 4. And if you wanted to say pi over 2, that is also just as good. Both are accepted equally with something like that. Okay, let's do our cosine function. So you could say y equals, amplitude's the same, period's the same. Our shift, though, it looks like there is no horizontal phase shift. We're starting right at the point 0, 1. So it's just going to be x, and then we know we have an amplitude of, we have a vertical displacement of 2. If you want, you could put that x in brackets like that just to be clear that that's separate from not saying x minus 2, but your teacher would understand that either way. Okay, we'll make this our last example for the day. So when you get to your homework, you'll have a chance to be able to work on any question from the assigned below, except for questions that have to do with tan. find a function in a cosine form that has a maximum and minimum point, and that's all the information they give us. So the maximum point is at 4, 2, and the minimum point is at 9, -6. So we know we have something that looks like that, but that's all we know. And these questions are pretty common. Let's start by saying our DACPA order works for something like this too. So if our max is at 2 and our min is at -6, if you're to average that out, -2, you'd be right in the middle where you could go up 4 and you could go down 4. So our displacement value will be at -2 and we'll have an amplitude of 4. Now just remember they're asking for a cosine function, not a sine function for this question. So cosine starts at its maximum value. So let's actually start it right here. Let's start it at that 4 right there. And the final thing that we're going to need to do is we need to figure out, well, what's our period going to be for something like this? So remember, when you graph a cosine function, going from the maximum to the minimum is half of the period. So going from an x value of 4 to an x value of 9, going over 5 units in this case, from 4 to 9, is representing half of the period, which means your whole period for something like this would be 5 doubled, you'd have a period of 10. Okay, so how do we do that? That's because this was a distance of 5 units, and that represents half of our period from here to here. And we want to say that means that our full period would be 10 units. Okay, so let's see if we have enough information right here. So you could say y equals, our amplitude was 4, cosine, our period is 10. So we'll say 2 pi over 10, you could say pi over 5. We've shifted 4 units to the right because a cosine value starts at its maximum point, which is right there. And we had a vertical displacement of down 2, so -2. And something like that would work out just fine. Okay, so we're going to stop right there. We're going to save graphing tan for next class. And then if you scroll down, you looked at what the homework was, you would say we're now able to do all of these questions except for anything that has to do with tan. We'll just save for the next class. So thanks for joining us.